So let's compare and contrast exponential models, the annual model versus the continuous model. For annual compounding, we have y equals a times b to the x. For continuous compounding, we have a equals p times e to the rt. Now we use different letters, but these columns are equivalent and these columns equivalent, these are and these are, with a slight difference here. So the initial value is a on top and p in the bottom. The growth or decay factor is either b or e to the r. The independent variable is x or t, which is often time, and the future value is y or a. Now b is 1 plus r, so b is the growth factor and r is the growth rate. This r and this r represent the same thing. When r is between negative 10% and 10%, 1 plus r is approximately equal to e to the r. This is just a rule of thumb. So let's take an example. When r is 3% or 0.03, 1 plus 0.03 is approximately equal to e to the 0.03. 1.03 is approximately equal to, and if you evaluate that, you get this decimal. So we can see that when r is 3%, b is 1.03, e to the r is 1.03045, etc. This is a little bit bigger. The two models differ only here and only slightly, especially when r is in this interval. When r is negative 3%, then 1 plus negative 0.03 is approximately equal to e to the negative 0.03. You see that 0.97, if you evaluate e to the negative 0.03, you get approximately 0.97. So at present, the population of Gambia is about 1.2 million people, and the population is growing at a rate of 3.7% compounded annually. So we're going to do this problem twice about how many people will be in Gambia in 10 years. We're going to do it on the left side annually, and then we're going to do it on the right side continuously. So there is where Gambia is on the western coast of Africa. So y equals a times b to the x, but b can be represented as 1 plus r. If r is 3.7% or 0.037, putting in a of 1.2 million and r of 0.037, after 10 years, the population is about 1.7257 million. Now, let's do the same problem using the continuous model. We should get approximately the same thing with a slightly larger population. A is equal to p times e to the r to the t, substituting 1.2 million in here, and r is 0.037. Remember that e to the 0.037 must be approximately 1.037, and it is. So we get, using this model, slightly bigger population, 1.737 million. When a problem talks about continuous compounding, you use this model. Otherwise, use the left model. These are very close but not identical results.